So welcome back. This is the 5th lecture. And today we're going to cover algebraic spaces and stacks. Yeah, in fact, I'm sort of speaking over really important moments in American history. The last 3 Wednesdays, we went from an insurrection to an impeachment and now to an inauguration. And that sort of mirrors the 3 developments in this class. You know, on 2 times ago, we introduced the fundamental notion of pre-stacks. And then we today are going to introduce stacks. Oh, last time we introduced stacks, and then today we're going to sort of complete this picture by introducing algebraic spaces, de Lee-Mumford stacks, and algebraic stacks. Right. Everything else we sort of we've covered so far. Yeah. So this is an important lecture, and but let's get started. I want to begin by reviewing first the terminology of pre-stacks and then stacks. And so, yeah, let's recap here. So we'll fix a site S. So S is our site. And then a pre-stack over S is just a functor. So it's the data of a category X together with a functor to S. And, you know, we think of objects in here as like maybe an A, and maybe there's a morphism to B, and these all live over elements of the site. So if you take the projection, this might be some object like a scheme S if you're working over the site of schemes. And then there were 2 main conditions in the definition of a pre-stack. The first was that, you know, pullbacks exist. So if you have a morphism S to T and an object B over T, there's an object A and a morphism from A to B over that morphism. And then moreover, that any map in X satisfies a universal property. And so the universal property for similar to the universal property for fiber products. And then building off that, we define a pre-stack. So if you turn to the right-hand side, we define a pre-stack to be a stack if certain descent conditions hold. So there's 2 conditions. The first is that morphisms glue uniquely in the topology of the site S. So maybe just to say, like, what that means is that if you have, say, an object S and you have 2 objects A and B over S, and you have a cover, and so you can consider the pullback of A to each SI. And then suppose you have maps phi from the pullback to B such that they're compatible, meaning that like phi restricted to the fiber product is equal, because they're morphisms, you can declare them to be equal. Then the condition is that there exists a unique map A to B, which restricts to the given maps. So that's the statement that morphisms glue. And then the statement that objects glue is also with respect to an tau cover. The condition is if you have objects AI over each SI and isomorphisms between their pullbacks. So here I'm really thinking of like the product of SI and the product SIJ. And then you have isomorphisms, say alpha IJ is an isomorphism from, let me write it this way. So you have an AI restricted to Sij, and you have an isomorphism alpha ij to the other pullback. So these are all objects over the double fiber products. Then, and they satisfy, and then this condition, you need them to satisfy a co-cycle condition, just like with gluing schemes or vector bundles. And then given that, then there exists an object A, which pulls back to the AI, and moreover, that these isomorphisms, that the isomorphisms alpha ij are the canonical ones. Right, so that's where we were. We had pre-stacks and stacks. We also had a few examples of these. So to any scheme, we can associate a stack. In fact, to any sheaf, you can associate a stack. And the objects of the stack are just maps. T, or let's say S to X. And this is, lives over the scheme S. And so, this is a stack over the big italicide. And then we had, that was our first example of how we view a scheme as a stack. And then we also had the stack of quasi-coherent sheaves where objects were pairs of a scheme together with a quasi-coherent sheaf. And then the main example in this entire course is MG, and here the objects are smooth families of curves, of genus G curves. And then morphisms or Cartesian diagrams. And what you already know just from the Zariski topology on schemes is that each of these three examples were stacks in the big Zariski topology. And a Tal descent, I was trying to argue last time that it actually implies that they're all stacks over the big italicide. Any questions before I move on?
So your point is that the stackiness over Zariski is kind of by definition of these various objects.
Yeah, exactly. It's sort of like if you look at the axioms for being a stack in the big Zariski topology, they just translate exactly to the gluing conditions you're already familiar with. And the only additional thing that we're using is this Tau topology. And therefore we need to use a number of descent results. And I used a few sort of descent results last time, and I'm gonna need similar results and more results this time. So I'd just like to begin by giving a brief recap and summary of descent theory, at least how we'll use it today. Okay, so here's my summary of descent. And so let's first look at this. So everything in descent relies on this one key algebra fact up here. And it's sort of this technical statement about having an exact sequence. But let me try to formulate the geometric version of this. So let's suppose that we have, let's just view this as map from spec B to spec A. And let's call this S prime and this S. And so the statement is if we take an A module, M, well, let's sheafify it and let's let that be the quasi-coherent sheaf F. And then if I take the restriction, the pullback, I'll just call that Fs prime or maybe F prime, I'll denote that. And then I can also consider the two pullbacks here. And the point is that the point is that there's a canonical isomorphism between the two pullbacks of F prime, such that under this canonical isomorphism, the sections that are identified are M. So in other words, this key algebraic fact is saying that if you're given a module M over the base here, you can actually recover it from its pullback by considering exactly sort of the kernel of this map. And so to state this even a slightly different way, so if you just let's just forget about F to begin with, the kind of the statement of descent is that you can recover F from this data. And then so moving on from this affine case, we can then have a more global version of this, which is what is featured in this bottom half. Oops. And here I'm just going to, so the descent it works more generally for faithfully flat maps, and sometimes for reductions you might want to add quasi-compactness hypothesis or a locally finite presentation, but let's just like restrict to Étale covers, because that's how we're going to apply it. So let's fix an Étale cover Si to S, and so then the global version of this key algebraic fact is that well, let's say it in two different ways. First, in terms of morphisms, and then in terms of objects. And so what it says in terms of morphisms is that giving a map between two quasi-coherent sheaves is the same as giving maps between their pullbacks that agree on the double pullbacks. And likewise with objects, that an object over the base is the same as objects over each SI and compatible isomorphisms. And so it is, this condition, it's this condition that allowed the stack of quasi-coherent sheaves to be a stack over the big Étale site. All right, so this, let me just write that here. All of this implies, or its equivalent implies that the stack quasi-coherent is a stack over the big Étale site. And then, okay, so we're going to build off this so we can descend modules. And if you think about so the next statement is that we can also descend affine morphisms. And so maybe here I'll draw a picture. So we have S, we have SI, and then we have these SIJs. And here, let's suppose we have affine morphisms from XI to SI, and then we have isomorphisms between their restrictions. So maybe, these are your alpha IJs, satisfying a cocycle condition. And since affine morphisms are defined by, OSI algebras, you can just think of them as modules together with, morphisms between the modules that give it the algebra structure. And so then if you apply the descent for quasi-coherent sheaves, you could descend, the ring defining Xi to at least to a module over S, and then you descend the algebra structure. And so you actually get an affine scheme that pulls back to Xi. And so you can descend affine morphisms in the Étale topology. And a special case of that are closed immersions, right? This would be the case where each Xi is closed in Si. And then note that in this condition, here, since you're comparing closed, since there are closed immersions, you don't need to worry about this cocycle condition. You could just say that Xi restricted to Sij, meaning the pullback under one of the maps is the same as the other one. And here, I should really be viewing these as products. So that's the first one application. So, and we can descend closed immersions. And maybe I just want to recall that last time, sort of we used this to show that MG was a stack because, if you'd had maybe over each SI, if you have a family of curves, CI, what we showed was that this embeds
Jarod,
into the projectivization of the push forward. Oops, running out of space. To the push forward of the third power. And then the idea was you look at this OSI module, you first descend that, so you can then find a quasi-coherent sheaf or even vector bundle over S, so that you take the relative projective space, and then since you have each of your curves are embedded CI, you can then descend these closed immersions to get a curve C over S embedded into that projective space. Right. This is all to say that that this, maybe I won't write it here. There's no space, but right, we use this case of descent to show that that MG was a stack in the big Étale topology.
Could you possibly explain why we have to take the third power? I've never really understood that because the second power already is ample.
Oh yeah, that's a good question. Right, so the question was, why do you have to take the third power? In fact, you could take any power that I think it has to be at least 3. But the point is, you need that the relative canonical sheaf that is very ample and not just ample, and it's a fact that the third power works. And certainly for hyperelliptic curves, you know, the sheaf of differentials itself is ample, but not very ample. I'd have to think about why the second power doesn't work. And when we get to stable curves, we'll have a similar phenomenon. And there I have examples. I know of examples where even the second power of the canonical is not very ample.
I think the second power just fails in genus 2. It's only for genus 2.
Oh, okay. Even for smooth curves.
I think that's right.
Right, and the last descent statement is going to be another special case of descending affine morphisms, which lead to principal G bundles. And since this is such an important notion, and I think a lot of people get stuck with it, let me remind you on the definition. Or let me, let's first fix G to T, the smooth and affine group scheme. And then the definition is that a principal G bundle, or just G bundle over T, is a map. So you have a scheme, maybe P with a morphism to T, and a G action on P over T, such that so that the map from P to T is G invariant. And then the condition is that it's just locally trivial, in the sense that then, you know, there exists an tau cover such that when you base change, sorry, I'm running out of space. So this is isomorphic to the trivial one, G cross Ti. G equivariantly. And so you really just think of this, you know, almost like topologically, you know, the fibers are G, but you have like a free action of G on the total space, and the quotient is T. And then therefore the corresponding statement for descending G bundles is the following. So this up in the upper left corner, we can descend G bundles, and we can descend them. And the reason this works, the key point is because G, we're assuming G is smooth and affine. So therefore that a G bundle P to T is necessarily affine. It's necessarily an affine morphism. So you first descend it just as an affine morphism, and then you descend all the other structure that makes it a G bundle. Essentially just using descent from morphisms. Okay, but actually more generally, you can ask, oh, so if I can descend affine morphisms, what else can I descend? I also know I can descend closed immersions, and therefore I can also descend that their complements open immersions. And so putting that together, you can descend quasi-affine morphisms. And in particular, you can descend morphisms of schemes that are separated and quasi-finite, because by Zariski's main theorem, they're necessarily quasi-affine. And I'm just stating this for later reference. Even more generally, we're going to use this later, but not today, is that you can actually drop okay, this is sort of technical, but in the definition of a quasi-finite morphisms of schemes, it's that it's finite type plus, you know, finite fibers. And you can have this more general statement where it's just separated and locally quasi-finite. Anyway, what I wanted to emphasize is what's on the right-hand side, which is sort of these consequences for descent. And so let's let P be a property where we have where we have effective descent. So like an open immersion, a closed immersion, it could be affine, quasi-affine, or this more general one. Or I should have been, yeah, maybe add, didn't write it here, a G-torser. And so then let's consider a diagram here, where in this diagram, S is a scheme, S prime is a scheme, F is just a presheaf. But you know that if you take the Cartesian product, suppose you know that if you take the Cartesian product, that F prime is a scheme, and this morphism satisfies property P. Then we're exactly in the situation, like because F prime is the pullback of a sheaf, you're going to have descent data for F prime over their pullbacks, and therefore you can apply this effective descent, and you can argue that it's identified with F, and so you get this conclusion that in fact that it implies that F is a scheme, and this map has property P. This is we'll use this statement today for G-torsors. Okay, any questions on this?
I feel like you need F to be a sheaf. I don't understand how it works if F's not if just a
Oh yeah, I'm only going to apply it when F is a sheaf. I kind of got worried with that pre-sheaf. Let's just say sheaf, just because I don't need the more general case. I was a little confused on that issue too.
So Jarod, I have a question about this descending maps, right? So you can't drop separated or locally quasi-finite?
No, not in general. Not in general. If you want to descend them as schemes, once we introduce algebraic spaces, we'll see that you can always descend as an algebraic space. And so, but it's actually, it's like really tricky question in general. If you're given an algebraic space, well, okay, which we'll define today. It's a tricky question to know whether a given algebraic space is a scheme. And these are some cases in which you can argue that it's a scheme, where yeah.
Cool, thanks.
So what is this Y?
Oh, that shouldn't be, that's a typo. That's S.
Oh, okay.
Sorry, yeah.
Sorry,
And
so could you repeat what is the statement here?
Right, the statement is this conclusion here. So like you have, so our hypothesis is that you have this Ital cover S prime to S, and that you have this morphism of sheaves from F to S, and then you consider this fiber product diagram, and then the conclusion is that if F prime is a scheme and the map from F prime to S prime has that property, then F is a scheme and the map F to S has that property.
Thank you.
This statement is sort of a reformulation of the other descent statements.
And the other implication, we almost always have it, right?
The other implication?
The opposite. Yeah, the other direction.
Yes, yeah, as long as that property is stable. Yeah, for all these properties are stable under base change. So yeah, so in fact, I think what the comment was that is in fact equivalence.
Okay.
Yeah. And I'm going to remind you of one more background statement that will also come up today, and that's the notion of Hilbert schemes. And so I'll just remind you of the main statement. And so yeah, so let me first I'll walk you through this. So we start with a projective morphism of Noetherian schemes, and we take a relatively ample line bundle OX of 1. We fix some polynomial with rational coefficients, and then we consider this moduli functor, where to a scheme S, you associate all closed subschemes of the pullback, which are flat which are flat over the base and with a given Hilbert polynomial. And then the amazing theorem, which this is like the starting point for all of moduli theory, is that it's represented by, this functor is represented by a scheme and it's projective over T. And like with descent, I mean, this is a statement that you can just black box. It's easy to internalize both like the content of the statement, and it's also easy to apply it. But like descent theory, I mean, it's also worth diving into the details once you have time. I mean, it's this sort of a nice, a nice argument, and that uses a number of important concepts like regularity and flattening stratifications. But I'm not going to say much more other than, is that we'll use this result. Any questions? Okay, let's get started with the new material. So I'm going to introduce some key definitions here. So on the left-hand side, we just define, okay, we've seen a similar notion before. So we say that a map of pre-sheaves or pre-stacks is representable by schemes if for every map from a scheme, the fiber product is a scheme. So in other words, I have F to G, I take a scheme S, and I'm requiring that this fiber product is always a scheme. And then once you have a morphism F to G that's representable by schemes, you can define any property. You can define properties of morphisms. So let P be a property of morphisms of schemes. The ones we'll use are surjective or tau. And then you can just say that a map of pre-sheaves or pre-stacks, which is assumed to be representable by schemes, has that property if for all maps from schemes, this induced map has that property from F cross GS to S. All right, so now we're going to use this definition to define algebraic spaces. So this is the first key definition of today. So an algebraic space, by definition, is a sheaf on the big Ital topology such that there exists a scheme U and a morphism U to X. Oh, is it? I didn't. Right. So it's a sheaf X on the big Ital topology, such that there exists a scheme and there exists a map from U to X, which is representable by schemes and Ital and surjective. Right, and we call, so yeah, this is the definition, and then we call U to X in a tau presentation. And I'm going to remark about this definition and the history and compare it to other definitions because, this is not as, it's equivalent to, but not quite the standard definition. And maybe I'll just note here that you can always cover schemes with affines. And so you can always find in a tau presentation where U is affine if you want. Right, and so now that we have algebraic spaces, I'm gonna go back to the left-hand side and generalize these definitions. So instead of saying that a map is representable by schemes, I'm gonna just say it's representable if for all maps from S to G, this is an algebraic space. So a map is representable if for every map from a scheme, or the fiber product is an algebraic space. And then we can also then define properties of morphisms between algebraic spaces. And I'm going to cheat by enlarging this. And so maybe so now that we have algebraic spaces, let's let P be a property of morphisms of schemes, which is a tau local on the source. What this means, maybe I'll just spell it out. A tau local on the source just means that if x prime is a tau and surjective, then then x to y has P if and only if the composition has P. That's what we mean by a tau local. And so if you have that property, just because algebraic spaces are defined, having a tau presentation by a scheme, we can therefore define a morphism, a representable map. So if you take a representable map F to G, you say it has property P. If for all maps from a scheme, maybe I'll draw the diagram down here. So you take a scheme, you take a map into G, you first compute this fiber product. Because this map is representable, this is an algebraic space. And therefore, you can choose, and then for any tau presentation of it, say U, this fiber product is wrong. It's G and S. Then you want the composition here to have that property. Again, yeah. So shortly we'll get into much more detail and background about properties of morphisms of algebraic spaces. But at least now we can talk about what it means for a surjective étale or smooth morphism of algebraic spaces.
Is there some kind of like comparison between different étale presentations of an algebraic space?
Well, you can
this is for all.
Right? If you have two different étale presentations and you take the fiber product, you get like a third one that refines both. And usually you use that principle to argue, for instance, that different constructions are independent of the presentation and whatnot.
Right on.
Also, why is it for the representable definition we're considering maps from schemes and not like maps just from any algebraic space S?
Oh yeah, it would be equivalent.
Okay.
Yeah. We'll get into all those technicalities and equivalences later. I just wanted to introduce the minimal amount of definitions necessary to define algebraic spaces and stacks.
So does it suffice to pick a single étale presentation to check P?
Yeah, almost always. Yeah, I mean, I think you technically you probably want to say it's also a tau local on the target. Maybe you need it to be stable under composition and base change. But yeah, usually you can check all these properties by taking a single cover. Yes. Yeah. And for all, certainly for surjective, étale, and smooth, you could change this for all to an exists. True.
Jared, in the second definition, do you need the map to be representable, or because you already defined what it means for representable to have property P in the first definition? Or I mean, sorry, the second definition. So do you want to drop it from the third?
No. I want. Yeah. So in this definition, I want it to be only representable by schemes. I'm defining properties of morphisms that are already assumed to be representable by schemes. And here I'm defining properties of morphisms that are between sheaves or stacks that's assumed to be representable.
By representable, you mean that the fiber product is an algebraic space?
Yes.
Oh, gotcha.
Yeah, that's what. So that's what I was trying to quickly define here. Maybe I should have just added that as a new definition too. Right. So really, I have 4 definitions here. The definition of representable by schemes, meaning that the fiber product of a scheme is always a scheme, is also just representable, which means the fiber product from a morphism from a scheme or equivalent from an algebraic space is then an algebraic space. And then we've defined properties of morphisms that are assumed to be either representable by schemes or just representable, right? And now, so now we can just define an algebraic, we define a Deligne-Mumford stack. Well, it's a stack over the big Étale topology such that there exists a scheme very similar to the above definition and a morphism U. So the stack is X, U to X, which is representable, Étale, and surjective. So it's almost like taking the definition of an algebraic space and replacing the sheaf with a stack. But there's one subtle difference. It's not really that important. I mean, I'll say a few more words later that like the difference is that is just declared to be representable and not representable by schemes. And this map here, we call an Étale presentation. Yeah, and then we just repeat this definition here. In fact, maybe I'll just cheat and copy it. And so we just, to move from a Deligne-Mumford stack to an algebraic stack. It's again a stack over the big Étale topology such that there exists a scheme. And so we only change the Étale-ness to smooth. And then this we call a smooth presentation. All right, yeah, so these are the 3 main definitions of today: algebraic spaces, Deligne-Mumford stacks, and algebraic stacks. But maybe before taking questions, let me recap sort of the history and compare these to the existing definitions in the literature. So first some history. Algebraic spaces were introduced by Artin and Knudsen in the late 60s, early 70s. There's some papers by Artin, and there's an entire book by Knudsen on algebraic spaces. And then around the same time, Deligne-Mumford stacks were introduced by, well, Deligne and Mumford, but they called them algebraic stacks. And then some years later, Michael Artin gave a more general definition and also called them algebraic stacks. And but I want to emphasize that there's like this warning on the right-hand side that our definitions are not really standard, and different authors, have different hypotheses on when they define algebraic stacks. So first and foremost, I think maybe this is the most important here, is that usually there's some sort of representability condition on the diagonal. But we will show actually that it's equivalent, that just with this weaker definition, it implies that the diagonal is always representable. I mean, this is which is of course, this is a well-known fact. I mean, I'm not, And so, yeah, one of the first things we need to show when we develop the theory of algebraic spaces and stacks is that the diagonal is representable, because it's an important property. And if you want, you can add that into the definition, but it's sort of, this is more streamlined, I suppose. And so, looking back at the history, algebraic spaces, when they were first introduced, they had, there was a quasi-compact hypothesis on the diagonal. And then Deligne and Mumford, well, they didn't impose that condition, but they actually assumed that the diagonal was representable by schemes. Or in other words, that there's an étale presentation by a scheme where that morphism is not just representable by schemes. But they also remarked in their paper that they were well aware that this wasn't the complete, the right definition in general. But they point out that it clearly sufficed for their case, because they were interested in MG bar, which is proper and has the diagonal has all of is a finite morphism. And maybe to point out that there's differences in the definition of Deligne-Mumford and the definition we're using only in really the pathological cases where the diagonal is non-separated or not quasi-compact. If the diagonal is quasi-compact and separated, then it's necessarily representable by schemes. And then finally, Artin had other assumptions in his definition. I mean, he basically assumed everything, assumed that everything was locally a finite type over an excellent Dedekind domain. Only because, and he only added this because what he was really interested in was giving equivalent conditions, like what are now called Artin's axioms, for showing that a given stack is algebraic. And at the time, sort of the Artin approximation result was only known for Dedekind domains, but now people usually refer to what Artin stacks as at least as those stacks that satisfy Artin's axioms. So in particular, if they're locally a finite type over an excellent scheme. But we won't use the terminology of Artin stacks. We'll stick to algebraic stacks. And maybe I'll point out that we are following both Olson's book and the Stacks project. Maybe the only difference here is that we use the big étale topology. Whoops, not the FPP topology. Okay, that was a mouthful. If you're seeing this for the first time, just ignore all these various hypotheses on the diagonal or whatnot, and take those three definitions as the main objects. I'll pause here for questions.
Does restricting to this étale topology make much of a difference?
Wait, I didn't hear that.
Is there much difference between this étale topology and FPPF topology?
Well, they're very different, but then, I mean, you just have so many more covers in the FPPF topology. But you can show in the end that when defining algebraic stacks that it's equivalent. But I really, don't want to get into those issues because they're technical, but you can read about them, and just going, between different sites, requires developing some background, and you can read about it in the Stacks project.
Okay, that answers my question. Thank you.
All right, so maybe I'll go back to the definitions so you can stare at them some more. These are the three key definitions: algebraic spaces, Deligne-Mumford stacks, and algebraic stacks. So now that we've defined what the geometric objects are, I should tell you what the morphisms are, and that's rather quick. So I just define maps of algebraic spaces are just maps of their underlying sheaves, or really pre-sheaves. And similarly, maps of the Lie-Mumford stacks and algebraic stacks are just maps of stacks, or even pre-stacks. And then I have this exercise here, which I recommend, is that you just show that we already showed that fiber products exist for pre-stacks. We showed that the fiber products of stacks is a stack, and now you're asked to bootstrap on that and show that if you have that the fiber product, that these notions, algebraic spaces, de Lie-Mumford stacks, and algebraic stacks are closed under fiber products. And maybe let me just say one other thing that will also just come up. Maybe this is an exercise, is show that any stack over, suppose you want to work in the relative setting of schemes over S. Can be viewed as a stack just over the category of scheme. So whoops. Yeah. In other words, you just forget about the morphism to S, but yeah. All right, so now we have some work cut out for us. I want to now show, the main goal now, after we've introduced the definitions, is to show two things. I want to show that quotient stacks are algebraic, and I want to show that MG is algebraic. Okay, and we're going to do them in order. First, we're going to try to show that, we're going to show the algebraicity of quotient stacks. And so on the left-hand side, I just have the setup. G to T is smooth and affine group scheme. And let's take an algebraic space. And if you want, okay, you maybe think, if this generality is too much, just take T to be, the spectrum of your favorite field. And then G is just like an honest, like smooth, affine algebraic group. And here, I'm taking U to be an algebraic space with an action of G. And this is defined, like, I've just introduced algebraic spaces. I haven't said anything else, but you can, this is defined exactly analogous to schemes. But if you want, you could just think U as a scheme if you want. And so that now we define something that we've defined, at least in the case when U was a scheme, we define the quotient stack. And this is a stack over the big étale topology in the relative case over T. But as I've just said, we could also view this as a stack over just schemes. And the objects are is the data of a principal G bundle together with a G equivariant map to the scheme U. And again, in the case that U is an algebraic space, you need to make this precise, but it's done in exactly the same as schemes. Right, so there's the setup. And then the theorem is that this quotient stack is an algebraic stack, and moreover, that this canonical projection from U is a G-torsor. And since since we're assuming G is smooth and affine, this map is representable, smooth, surjective, and even affine. In particular, this is a smooth presentation. Right, so we need to show this. Okay. So let's set Okay, so let's set X to be this quotient. And so let be a map from a scheme. And we can consider, so I do have a morphism from U to U mod G. And, oh, sorry, that was written as X, right? U mod G. And then if I take S to X, let's define the fiber product as US. And what we need to show is that US to S is a G-torsor. Because that's exactly what it means for this cover U to the quotient to be a G-torsor. And in particular, all of these maps, once you show this, all of these maps are smooth and affine. And in particular, US is, we need to show that US is a scheme.
Shouldn't US, sorry, is U here is just an algebraic space, not a scheme, right?
Wait, sorry, can you repeat that question? I didn't get it.
Yeah, sorry, I'm just trying to wrap my head things. So U here is just an algebraic space, it's not a scheme.
That's right.
And so this map from U to X, are we wanting it to be representable or to be representable by schemes? So I'm confused about if US should be a scheme or an algebraic space.
Here we're working more generally with U as an algebraic space. Okay, so yeah, I think you raise a good point in that. Right, what we want this map. We want this map to be representable by. We want it just to be representable, period, not necessarily representable by schemes. Yeah, but I think your point is that then I mean in the definition of a stack, I have a smooth presentation by a scheme, not by an algebraic space. And so if you want, if you like, you can always further, like if this is just an algebraic space, you can always find a further ital cover where that's a scheme. And so then, does that answer the question?
Not quite. Yeah, so I'm fine with that. I just mean this U sub S. Do we want it to just be an algebraic space, or do we want it to furthermore be a scheme? This
in the end, we want to show, yeah. So in the end, in particular, we want to show, yeah, that US is a scheme, affine over S.
Yeah, but is this special to the? Is this? If I'm understanding, this is special to like this quotient. Like in general, we would just want this to be an algebraic space, but for this quotient, it actually turns out to furthermore be a scheme.
Yes, in this case, because of the assumptions we're making on the group scheme, that's right. So in general, you don't expect all your presentations to be, say, affine, but in this case, our presentations are even, the morphism from U to X is even affine. Yeah, it's a good question.
Okay, cool. Thanks. This helps clear things up.
All right, and now, okay, so and now what do we know? Well, we know that this quotient stack is the same as taking the pre-stack and taking the stackification. So what that means, like that, if I have S to X and I have this presentation, what that means is that there actually exists some S prime ital cover and a morphism to U such that this is too commutative. In other words, like every G bundle is trivializable after an ital cover, and a morphism from S to X, factors through this cover if and only if that G bundle is trivial. And so you can always, after trivializing, get an ital extension that maps to U. And then we're going to use this. We form the following cube, where I first remember we have this G cross U to X to X. Remember we have this Cartesian diagram already. And now I want to compare it to what's happening. I have S, I have S prime. So I first take US, this pullback, and I can also take S prime, and then I can take US prime. And, in this diagram, let's see, that everything is Cartesian in this diagram except for the left and the right. So the top, bottom, back, and front are Cartesian. And let's see what we know here. Remember, we're really interested in knowing stuff about US. And at the moment, we just know it's a sheaf. But what else do we know? I mean, we know that this morphism from G cross U to U, we know that this is a G bundle. It's a trivial G bundle, and therefore its pullback from US prime to S prime is a G bundle. And so if you just look at the back Cartesian square, this here is a scheme. This is a scheme. And this is an Ital's rejection. And so we could use this effective descent for G-torsors. I mean, the statement that we had was that, like if you have the sheaf US over S, and after an Ital cover, if you know it's a G bundle, then it's already a G bundle. And so we use that descent to get that US to S as a G bundle, and that's exactly what we wanted to show. All right, now let's use this now to show maybe the more complicated statement. Well, yeah, first, before we move to MG, I just want to discuss kind of a nice consequence of this. And now if G is a finite group, then if G is a finite group acting freely on an algebraic space X, then the quotient sheaf is an algebraic space. And so here, note that here, like the map from X to X mod G, because G is finite, is actually an Ital presentation. And so the upshot here is like free actions is that free actions of a finite group on a scheme exists as an algebraic space. And this is one of our motivating factors for the first point to introduce algebraic spaces, because, you know, sure, if you have a finite group acting on a quasi-projective variety, you can take the quotient. But there are some subtle examples where you can have something acting on a finite group acting freely on a proper but not projective variety, such that the quotient doesn't exist. And since like finite group actions are ubiquitous in algebraic geometry, we want to be able to take the quotients. And this says that we can as an algebraic space. But it also says something more. It says that this notion of an algebraic space is sufficiently nice in that it's closed under taking quotients. So we don't we've introduced algebraic spaces so that the quotient of a free action of a finite group on a scheme exists as an algebraic space, but but we can stop there. We don't need to go further and introduce a more general notion because it's closed under taking quotients by free actions. And now I want to turn and try to use the algebraicity of quotient stacks to show that MG is algebraic. So if G is at least 2, my goal is to show that MG is algebraic. And to recap, we already know it's a stack in the big étale topology. So what we need to construct is a smooth presentation. And our strategy is to show that MG is identified with a certain quotient stack where H is some Hilbert locus of parametrizing like 3 canonically embedded smooth curves. Because once we show this, we already know that right-hand side is algebraic by the former result. And this will allow us to conclude that MG is algebraic. Okay, so let's try this. So let's consider a family of curves, C to S, smooth family. Let's let this be pi. And what we know is that, that we can embed this into the relative projective space of the third canonical. And we know also, I'm just trying to just state everything we know so that we can, so that then the proof looks more natural. So this is of rank 5G minus 1. And note that on fibers, what does this diagram look like if we restrict to a fiber over a point in the base? Well, then you actually have an embedding into the projective, like then this is spec K over S. But then this vector bundle is trivial, so it actually embeds into just projective space of dimension 5G minus 6. And moreover, the Hilbert polynomial you can compute just by Riemann-Roch is, P of n is 6n minus 1, G minus 1. Okay, and now we define, let's define H as the Hilbert scheme in projective space of closed subvarieties or closed subschemes of projective space of Hilbert polynomial P. Well, I think. And this we know is projective over Z. And we also know by Grothendieck's theorem that it's representable, so we can take the universal family. So over H, there's a universal curve C, which embeds into here. This is the universal family. And now the main idea, what we want to do is we just want to restrict. We want to look at the locus in H where the family of smooth curves tricanonically embedded. Because I mean, this H itself is huge. You know, I mean, like Hilbert schemes can have awful singularities. So the curves that they're parametrizing certainly may not be smooth. They may not even be pure dimension 1. So we want to restrict to nice ones. And so here's the statement a more precise statement that we need. Whoops. Right, so the conclusion, so the claim is that there exists some H prime in H locally closed. And such that it contains all points H with the following 3 conditions. The first is that the fiber is smooth and geometrically connected. Those are the curves in MG that we're parametrizing. And moreover, we're going to have this, we can assume that, well, we want to assume that the third canonical and the O of 1 differ by the pullback of a line bundle. Maybe the simpler, like maybe on a fiber, so like over a fiber H in H, this is just the condition that, that if I take the third canonical of that fiber, it should be isomorphic to the O of 1. So we don't want our curves to be embedded by some other line bundle. We want them to be tricanonically embedded. But not only that, it's not enough just to say that they're embedded by the right line bundle. You want them to be embedded by the complete linear series, not by some other linear series. So moving on to C, what we want is that the natural map from projective space to the restriction, and O of 1 here, we know is isomorphic to the third canonical. And I want that map to be an isomorphism. So this is exactly what it means to say that it's embedded via a complete linear series. So now I have two tasks. Oh, and not much time, but let me try to finish. First, I'm first going to prove the claim, and then I'm going to use the claim to get algebricity. So here's my proof of the claim. So remember, so we have this universal family over H that embeds into projective space. And for A, so maybe I'll break this into two parts, the smoothness and the connectedness of the fibers. For the smoothness, we just note that this is just a general property that if I look at the point such that the fiber is smooth, this is an open condition. Certainly it's an open condition in the source, but our maps here are proper. So if you look at the closed locus in C where it's not smooth and take its image, that's closed in H, and that's exactly the complement of this open. And now the geometrically connectedness is a little trickier, but you can take the Stein factorization, which is say C. Let's let this map be pi to the spectrum, relative spectrum of pi push forward of OC, and this lives over H. And this map has geometrically connected fibers, this map here. And so if we let's let lambda be the induced map from OH to the push forward of O of C. And then the condition in H that the fiber is geometrically connected is precisely the points in H where this map lambda, where lambda is an isomorphism. Isomorphism at H. So in other words, this is precisely the locus of H where you remove the support of the kernel and the co-kernel. Right, because maybe I should point out that, this is a proper morphism. So this push forward is coherent. So this is a map of coherent sheaves. And so the kernel and the co-kernel have closed support. So when you remove this, you get an open locus. So that handles case A. So in other words, let's just assume now, we can assume now that that the fibers are smooth and geometrically connected. The second fact, B, is the tricky one, and here we need to use something. And so here's the result we need. So the way I think about this result is that, okay, so then first let me state the hypothesis. We have a morphism X to Y. with some conditions, and a line bundle L over X. And so the conclusion of this theorem basically says that the locus in Y where the fiber of L is trivial is a closed locus. More precisely, it says that, yeah, there's a closed subscheme such that where the fibers are well, not exactly isomorphic, but differ by the pullback of a line bundle. And it satisfies this functorial condition. Right, and yeah, so I won't prove this, but this follows from some results in cohomology and base change. I mean, like the basic idea is you want to show that the locus where a line bundle is trivial is closed, and like you try to redefine this condition by sections of the line bundle and its inverse, right? Because trivial line bundles have one section, and so does their inverse. This puts constraints and use upper semi-continuity and to argue that it's yeah, that is true. And I did want to say I won't use this following fact, but I think it's sort of a nice reformulations of it. So I want to say that this theorem is also equivalent to the following fact. It's equivalent to the separatedness of the relative Picard functor, where the schemes over Y to sets, where an S to a Y gets mapped to pic of X cross Y over S, and then you mod out by things from the pullback. And I like this. I'm just saying this because it kind of it addresses this fact that sometimes complicated statements like the one above, if you reinterpret it in the moduli perspective, it has like sort of a nice translation. But anyway, this theorem is precisely what gives us B. And then for C, let me just say it quickly. I really am running out of time. Like you want to consider the relative version of being a complete linear series, and so you study the map from to the push forward, and you look at the locus in H, where this is an isomorphism. And like before, you just throw out the locus, the support of the kernel and the co-kernel. And so this shows C. But I did want to get to the sort of the main finale here, which was using this claim to show that MG is algebraic. And so then if you just give me 5 more minutes, there won't be much time for discussion, unfortunately. Okay, so given this claim, I want to note that there exists a functorial action of PGL 5G minus 6, which is identified with the automorphism group scheme of projective space. Wait, I think I'm off with this. Oh, maybe this should be a 5. There's a functorial action on H where you just like, because H is parameterizing things embedded, closed things embedded into projective space. You know, if you have an automorphism of projective space, you just move that subvariety subscheme by that element. And H prime in H is invariant. And our goal is to show that MG is isomorphic to H prime mod this group. And it's actually not that bad. So I'll do it in maybe 3 steps or 4. Let's see. We first construct a map from H prime mod PGL 5G minus 6 from the pre-stack to MG. And here, it's not so bad. If I have a morphism from S to H prime, remember these were the objects in the pre-stack. I need to send it to some family of curves. But remember, H prime is a sublocus of the Hilbert scheme. So this itself corresponds to a family of curves over S and an embedding into projective space. So we can just send this to the corresponding family. So that's the first thing. And the second thing to note is that this map is fully faithful. And the reason is that an automorphism of C over S induces an automorphism of the relative canonical, because after all, it's canonical, and therefore an automorphism of projective space. In the case, because, and therefore, yeah. In this case, like when, in the right-hand side, because we have an embedding into projective space, this, the push forward of this is actually trivial. So, right. Yeah, so you check that this map is fully faithful, and then by the universal property of stackification, there exists a map H prime from the stack to MG, and it's also fully faithful. And this follows from a simple exercise that if you have if the map from the pre-stack was fully faithful, then the map from the stackification is also fully faithful. So the only thing that's missing is the essential surjectivity, because after all, yeah, we want to show that this is an isomorphism. But maybe I'll move over to here. Well, to show it, like we need to show every family is in the image, and it suffices to show that for all families of smooth curves, that there exists an étale cover such that the restriction C as I is in the image. This is sort of like saying what it means for like a surjective map of sheaves. You know, not any section lifts, but it locally lifts. And then because both things are stacks, if you know it locally lifts, then you can glue everything together using the fully faithfulness. But the point now, the point now is, well, all you do is you take like you have this map C to S, and you consider the push forward of the third canonical. You always have an embedding into that relative projective space, but you choose a Zariski cover. You can even choose it to be a Zariski cover, where this vector bundle is trivial. Where it's trivial. You just use a trivialization of the vector bundle that gives you maps not into honest projective space, and therefore corresponds to an element of the Hilbert scheme. Wow. Okay, that took longer than I thought, but I'm gonna end here and stop the recording.